Hello everyone, in this video, I'm going to discuss students' t-distribution. According to the central limit theorem, the sampling distribution of a statistic, like a sample mean, will follow a normal distribution if the sample size n is sufficiently large, meaning to say, it is greater than 30 or 30. Therefore, when we know the standard deviation of the population, we can compute a z-score and use the normal distribution to evaluate the probabilities with the sample mean. So at the end of this video, you must be able to illustrate the t-distribution and enumerate its properties. Also, you must be able to identify percentiles using the t-table. So the student's t-distribution is a continuous probability distribution, and it is used to estimate population parameter when the sample size is small. Meaning to say, the sample size is less than 30, or when the population variance is unknown, which usually happen in a real life situation. Students' t-distribution was developed by William C. Gossett in 1908. He used the pseudonym or pen name student when he published his paper which described the distribution. That is why it is called students' t-distribution. Suppose you are about to draw a random sample of n observations from a normally distributed population. You previously learned that z equals the sample mean minus the population mean all over the population standard deviation divided by the square root of the sample size, which is this formula. If we're going to recall the formula, we know that z is the z-score, x bar is the sample mean, mu is the population mean, and sigma is the population standard deviation. And n is the sample size, have the standard normal distribution. And we must take note that if we are standardizing a single observation, meaning to say the value of n is equal to 1, it will turn to this one. Z equals sample mean, or the score rather, minus the population mean divided by the standard deviation, since the value of n is equal to 1. Okay, you can use this concept to construct a confidence interval for the population mean, mu. But in practice, you encounter a problem, and that problem is that you don't know the value of the population standard deviation or the population variance. The standard deviation for the entire population, sigma, is a parameter, and it is usually unknown, so the formula cannot be used. If that happens, the next best thing to do is to use an estimate, which is the sample standard deviation, S, instead of using the population standard deviation, sigma. Now, if we're going to take a look at this, we are going to use this one instead of this one. And if we're going to take a look at those two, they have almost no difference aside from the standard deviation. In here we use population standard deviation, and here we use the sample standard deviation. Another thing that we must take a look at is the change in the formula. The quantity population standard deviation is a constant, but we don't know its value, so we need to use the sample standard deviation, which is a statistic. And this statistic has a sampling distribution. And most of the time, its value is different from sample to sample. And so, this one do not follow the standard normal distribution. It is normal, but it is not the standard normal. Now, this quantity is labeled as T because it has a T distribution. When you are sampling from a normally distributed population, the quantity T is equal to the sample mean minus the population mean all over the sample standard deviation divided by the square root of the sample size. We should also take note of the other variable which depend on the sample size, which is the degrees of freedom. So this degrees of freedom is needed for us to identify the t-value in the later part of our discussion. Now, to obtain the degrees of freedom, we just need to subtract 1 to the sample size. Meaning to say, if we have the sample size 25, the degrees of freedom is 25 minus 1, which goes to show that is 24. And similarly, if we have the degrees of freedom 16, therefore the sample size is 17 because 17 minus 1 is 16. So, what does the distribution look like? As I have said a while ago, if you look at the statistic, this one, it looked like Z statistic as a standard normal distribution, except that you replace the population standard deviation sigma by S. And again, as I have said, that is only the difference between Z and T. Also, since we are estimating a parameter with a statistic, so there is a greater variability. Our T distribution is going to look like the normal distribution except the greater the variance. So we have here a plot of standard normal distribution in black, this one, and t-distribution with 3, 5, 20, and 30 degrees of freedom in red, green, violet, and blue respectively. You can see that both z-distribution and t-distribution are symmetric about the 0 and bell shape. But the t-distribution have heavier tails. This one, they have heavier tails, or more area in the tails and lower peaks. They have lower peaks. The exact shape of t-distribution depends on the degrees of freedom or the sample size. The figure above, or this figure rather, tells you that as the degrees of freedom increases, the t-distribution tends toward the normal distribution. At 30 degrees of freedom, as we can see here, the blue curve might look very close to the normal curve. But if you look very closely, if we're going to zoom this, we will see that the t-distribution still has a slightly heavier tails and slightly lower peak. But if you let those degrees of freedom continue to increase, the t-distribution is going to get closer and closer to the standard normal distribution.